here in this slide, here in the table, in the first column, if you see, the structure of the controller has been presented, controller structure, and in the second column, the transfer function associated with the controller structure that has been presented, and in the last column, that is in the third column, the make and model number of a PID controller. So that industrial type PID controller has been presented. Let me repeat again. In the first column, the structure, the controller structure, there are many controller structures available in the market, in the control literature, and that has been adopted in industry, I would say. So the first column is the controller structure. The second column is the transfer function associated with the controller structure. And the third column is the make and model number of the industrial PID controller, which had used that particular structure. Okay. So that's and if you see the second row, in the second row, first column, the structure has been named as ideal PI, and the transfer function associated with that ideal PI controller is presented in the second column, which is GC of S, which is the transfer function of a controller. That here, if you see, which is it is represented as Kc into 1 plus 1 by tau is. That's the transfer function of an ideal PI controller. And the transfer function of the ideal PID controller has been shown in the third row. So which is Kc into 1 plus 1 by tau is plus tau is. So this is a transfer function, I would say, textbook version of a PID controller is shown in second as well as in third row. So if you see any standard textbook, the transfer function representation of a PID controller, PI or a PID controller, normally you will see this, it will be reported. Whatever is reported in the second column, that you will see in a standard textbook. But here, let me explain what are all the problems associated with an ideal PID controller transfer function. This ideal PID controller transfer function is not physically realizable. It's not physically realizable. The reason why it is not physically realizable is, for a transfer function to be physically realizable, the degree of denominator polynomial always should be greater than or equal to the degree of numerator polynomial. So here there is a numerator polynomial in S and a denominator polynomial. If you see the degree of denominator polynomial, it will be 1, whereas the degree of numerator polynomial will be 2. So as a result, this transfer function is not physically realizable. So ideal PID controller transfer function is not physically realizable. So that's what I wanted to highlight. And as a result, to make it physically realizable, many variations have been introduced in the control literature. And in the fourth row, the first, like what we have done is here, a realizable PID controller transfer function has been represented in the second column. And the name of the controller structure is ideal PID with filter. By adding a filter in series, by adding a filter 1 by tau of S plus 1, a lag filter in series with an ideal PID, we are able to get obtain a realizable PID controller transfer function. And if you see here, the degree of numerator polynomial will be equal to that of degree of numerator polynomial. So here, the degree of numerator polynomial will be 2 and degree of denominator polynomial also will be 2. So as a result, this transfer function is physically realizable and it has been named as ideal PID with filter. And this transfer function has been converted into an algorithm. So you will be able to, so this transfer function has been converted into an algorithm, and you can see in Allen Bradley PLC, programmable logic controller, GE Fanuc 9030, 9070 programmable logic controllers, and in Honeywell TDC 3000, which is a distributed control system, and Yokogawa field control station. This is again a distributed control system or a single loop controller or a multi-loop controller. In all this, the Allen Bradley, G. Fanuc, Honeywell, Yokogawa are considered as major industrial automation players, and in those PLCs and distributed control system, this ideal PID with filter has been realized in the form of an algorithm. So and these PID controllers are widely used in process industry, and with the help of these PID controllers, you will be able to control the process variable. It could be speed control, or it could be flow control, or pressure level, whatever be the variable, pH. So with the help of the PID controllers, you will be able to control the process variable at the desired set point. And so as I mentioned earlier, there are many ways by which what will happen. You can convert an ideal PID. Ideal PID is not physically realizable. You can make it physically realizable by making suitable modification. So here in the first case, a filter has been added in series with an ideal PID. And in the second case, the TDS term, if you see here in the ideal PID, TD times S, that is basically a pure derivative term. Pure derivative term is not physically realizable. So instead, this pure derivative term has been approximated. In the last row, if you see, TD times S is replaced by TDS by TD by NS plus 1. So we have added again a lag filter to the TDS, that is a pure derivative term. As a result, I would say this is nothing but it's a lag lead filter or an approximate differentiator, not an ideal differentiator. In ideal PID, we are using a pure differentiator here, or an ideal differentiator, which is not physically realizable, whereas here tau ds by tau dns plus 1 can be viewed as an approximate differentiator or a practical differentiator. So with the help of this suitable modification, ideal PID which is not physically realizable, which is not a physically realizable transfer function, it has been converted into a physically realizable transfer function. So that is called filtered derivative type PID. The name of that controller structure is called filtered derivative type PID, and this has been realized again in the form of an algorithm in Bailey Net 90 PID controller, Foxborough, Modicon, Siemens, and so in various what I would say, these are various products available in the market where they have used this the transfer function, which is shown in the second column, has been converted into an algorithm. And the algorithm has been realized, has been ported on the processor, it could be a microcontroller, could be a DSP processor. So the algorithm has been ported onto the respective hardware, and with the help of the PID algorithm, you'll be able to control the process variable. And if you see here, any textbook version, there are 3 parameters associated with the PID controller. They are nothing but Kc, tau I, and tau d. Kc is proportional gain, tau I is integral time, tau d is derivative time. And if you see the fourth and the fifth one, the fourth row and the fifth row, the second column, if you see, you have an extra parameter tau f in the ideal PID with a filter, and we have an additional parameter n in the case of filtered derivative type PID control. So there are, and if you see here, you have one more extra parameter tau f in the case of ideal PID with filter, whereas in the case of filtered derivative type PID, we have an additional parameter n. And all these parameters, that is Kc, tau I, tau d, and tau f in the case of ideal PID with filter, and in the case of filtered derivative type PID, Kc, tau I, tau d, and n, they have to be optimally, they have to be selected. So that is falling into the category tuning of a PID controller, tuning of or a design of a PID controller. I'll come back to that in my later. Later I will discuss in detail about the various parameters associated with the controller. But in a nutshell, a PID controller, how it does corrective action, that if I want to put in a plain English, the corrective action is based on what is happening at the moment, what has happened in the past, and what will happen in future. So the 3 action, past, present, and future errors, they are judiciously, they are mixed actually. The weighting, the weights associated with the present error is proportional action, that is KC, proportional gain, and the weight associated with the integral action is KC by TI, which we call it as integral gain, and the weight associated with the derivative action, that is based on the rate of change of error, dE by dt, that is KC times TD. So all these three actions have to be judiciously, they have to be optimally, they have to be weighted, and by judiciously mixing all the three actions, we'll be able to get satisfactory servo performance as well as regulatory performance. I would say either servo performance or regulatory performance, or sometimes what you can do is like you'll be able to achieve both servo and regulatory. But here, I would say we can achieve either satisfactory servo performance or regulatory performance using these four parameters. So the corrective action, again, let me repeat, the corrective action is based on the weighted combination of past, present, and future error. Or I would say an anticipated error. Okay, that is the future error here. What I would say is basically the anticipated error, and you can find that by determining the rate of change of error and E of t, what you can do is that you will be able to predict what will be the value of error at t plus td instant. So based on that, the current error and the rate of change of error, so that's what I call it as an anticipated error or a projected error at future time. Or okay, so based on that, the controller is taking corrective action and trying to maintain the process variable at the desired set point. So this in the control literature, it is called an ideal form of PID controller or a parallel form of PID controller. And in the next slide, I'm going to explain in detail about another form that is called a classical form or a series form or an interacting type of PID controller structure, whereas the earlier one, what we call it as a parallel form or a non-interacting form. And here, if you see the second one, in the second column, here what I have reported is the transfer function of a series PID controller. And again, if you see this transfer function, it is not physically realizable. To make the transfer function physically realizable, a lag term has been added. So tau d s plus 1 is not physically realizable. That's a lead term. It's not physically realizable. To make it realizable, a lag block has been added or a lag term has been added. So this can be viewed as TDS plus 1, tau d s plus 1 divided by tau d ns plus 1 can be viewed as a lag lead filter. So a lag lead filter in series with a PI controller. If you see the earlier slide, ideal PI is nothing but KC into 1 plus 1 by tau is. So by adding a lag lead filter in series with an ideal PI, a series form has been realized. And this transfer function is physically realizable. And this transfer function has been converted into an algorithm. And that algorithm has been, the algorithm has been ported on various processors available in the market. And in Toshiba, in Foxborough, and in Honeywell, UDC 6000, they make use of this series form PID controller. And with the help of this controller, the controller tries to maintain the process variable at the desired set point. And here again, you see there are 4 parameters, KC, tau I, tau D, and N. So that is with respect to, so this is one way of making this transfer function physically realizable. The other possibility is what we try to do is we try to, instead of using the ideal differentiator, we use a practical differentiator, that is tau d into s divided by tau d ns plus 1. And so in here, so we are not using the ideal differentiator, we are using a practical differentiator. By using a practical differentiator, we are making the transfer function physically realizable. That is ideal series, the the series PID controller transfer function, which is not physically realizable, has been converted into a realizable transfer function. And this again can be converted into an algorithm. This can be converted into an algorithm, and that algorithm, if you see Bailey as well as in Fisher, they have used this PID controller transfer function has been converted into an algorithm in the Bailey as well as in Fisher industrial type PID controller. So, and if you see here in Honeywell UDC 6000, the value of n has been set to 8. In the case of Foxborough, the value of n has been set to 10. But instead of setting the value to 10 or 8, my suggestion could be like KC, tau I, tau D, n also has to be optimally selected. At the time of design stage itself, if you are able to properly select the value of n, then definitely you can improve the performance of the controller. But in certain products, they have fixed the value of n. There you will not be able to make any modification. But in certain other products, n is considered as a variable, and the user can set the value of n, like KC, tau I, and tau. But in most of the industrial type PID controller, they have set the value of n to 10 or 8. And you can see in the earlier one also they have set, like in Modicon, there is a lower bound value and upper bound value. Lower bound value is 2 and upper bound value is 30. So user can select any value between greater than or equal to 2 or less than or equal to 30. And in Siemens, they have set the value of n to be 10. So in certain products, user can set the value. In certain products, n has been prefixed. The value of n has been set to a constant value. So here, so this is a classical type PID controller, and there are so far what I've done is like I've discussed two forms of PID controller. The first one is an ideal or a non-interacting or a parallel form PID controller. The second one is a classical or a series or an interacting type PID controller. So these are the popular PID controller structures available in the controller literature, in the control system literature, and we should not, while teaching or while carrying out research, we should not use the ideal one or the series form of PID controller, which is not physically realizable. Either the second one or the third one we should use in the case of series form, whereas in the case of a parallel form, you have to use the ideal PID with filter or a filter derivative type PID controller. So here for teaching students, as well as if you wanted to implement PID algorithm as a part of if you want to implement PID algorithm as a part of research, you should use ideal PID with filter or a filter derivative type PID controller, not an ideal PID controller. Similarly, in series form, if you wanted to use series form, then you should use a lead lag filter in series with a PID controller, or an approximate differentiator plus 1 plus approximate differentiator times an ideal PID controller you should use, and that you should realize in the form of an algorithm. So far I have discussed two PID controller structure, and the make and model number also I had mentioned in my presentation. So far what I have discussed is a single degrees of freedom PID controller structure. Let me clarify what I mean by single degrees of freedom PID controller structure. If you use a single degrees of freedom PID controller structure, you will get either satisfactory servo performance, set point response, or satisfactory load response or disturbance rejection performance. You will not be able to get satisfied. You will not be able to simultaneously satisfy both servo performance and regulatory performance. Hello. You will not be able to simultaneously satisfy both servo performance and regulatory performance if you use a single degrees of freedom PID controller structure. Whereas the one which I'm going to discuss in this slide, with the help of this 2 degrees of freedom PID controller, you will be able to achieve both satisfactory servo performance and regulatory performance. Or in other words, without sacrificing a load disturbance rejection performance, you can improve the servo performance. That's the power of this 2 degrees of freedom PID controller structure. and the transfer function associated with 2 degrees of freedom PID controller structure is presented in the first table. Here, this capital U of S is nothing but the output of the controller, and which is a function of R of S. R is nothing but the set point, and Y of S is the variable which you would like to control. So Y is nothing but the process variable. So U of S is a function of R of S and Y of S. And if you see here, in the first, the transfer function relating U of S and R of S, if you see, there are 6 parameters: alpha, beta, tau I, tau D, and N. So, and also Kc. So there are 6 parameters associated with what I would say U of S by R of S. If you take U of S by R of S, and there are 4 parameters associated with U of S by Y of S, Kc, tau I, tau D, and N. So in order to get satisfactory regulatory performance or disturbance rejection performance, you have to properly select the value of Kc, tau I, tau D, and N. By properly selecting the value of Kc, tau I, tau D, and N, you can get satisfactory regulatory performance. And that same value again you will use here. You will use that Kc, tau I, tau D. But when you give a set point change, you may not get satisfactory servo performance. So to improve the set point performance, the servo performance, to improve the servo performance, what you have to do is that you have to properly select the value. You have to adjust the value of alpha and beta. By properly adjusting this value of alpha and beta, you can improve the servo performance without sacrificing regulatory performance. That's the power of this 2 degrees of freedom PID control structure. So there are 6 parameters. They are alpha, beta, N, Kc, tau D, and tau I. With the help of this, you will be able to achieve both satisfactory servo performance and regulatory performance. That's the power of this 2 degrees of freedom PID controller structure. Whereas if you use a single degrees of freedom PID controller structure, either you get satisfactory servo performance or regulatory performance. You will not be able to satisfy both. And this transfer function, again, it has been realized in the form of an algorithm, and you can see in Bailey net 90 PID, this transfer function has been realized in the form of an algorithm. This has been named as an ISA type PID controller. ISA is nothing but International Society of Automation. It's a professional body, and they set the standards for automation, and this structure has been recommended by ISA. So there is a PID standards available, and ISA has proposed this particular standard. And in the second table, I have the 2 degrees of freedom again, and variant of 2 degrees of freedom PID controller has been presented, and that has been named as PI-D. PI-D. Here, how to interpret this acronym PI-D? Let me explain. The PI proportional integral action is based on error, and derivative action is based on process variable or derivative based on measurement. So, and the transfer function associated with this is presented in the second table, the second row. And by setting the value of alpha and beta, alpha as 1 and beta as 0, you can get this transfer function. So the transfer function which is presented in the first table is the most generic one. By setting the value of alpha equal to 1 and beta equal to 0, you will get a variant of 2 degrees of freedom PID controller, which is PI-D. So where here, let me repeat again, the proportional action and integral action is based on error, whereas derivative action is based on process variable, that is based on Y. And the advantage in using this particular structure over the earlier one is that is the earlier one, what I would say is the single degrees of freedom PID controller structure, is that you will be able to prevent derivative kick if you use this structure. If all the 3 actions, that is proportional, integral, and derivative action, if it is based on error, then whenever a set point, abrupt change in set point is made, then you will get an abrupt variation in the controller output, you will get spikes in the controller output, which will affect the life of the final control element. So as a result, in order to prevent derivative kick, derivative action should not be based on error, it should be based on measurement. So and thereby you will be able to enhance the life of the final control element. You will be able to protect the final control element. So that's the power, the advantage of this 2 degrees of freedom PID controller. So abrupt variation in the controller output can be avoided. That is what we call it as a kick. Derivative kick can be avoided if you use a 2 degrees of freedom PID controller, that is PI-D. And this is again, it has been realized in Allen Bradley PLC, Yokogawa single loop PID controller, as well as in Omron PLC. So this is I have explained the advantage of 2 degrees of freedom PID controller. In this slide, I have explained what is the advantage of a 2 degrees of freedom PID controller over a single degrees of freedom PID controller. And another variant is presented in the first table in this slide. Here, the integral action is based on error, whereas derivative action and proportional action is based on process variable, again based on y. So the integral action alone is based on error. So with the help of this IPD controller structure, that is IPD PID controller structure, you will be able to prevent proportional kick as well as derivative kick. So you can avoid kick in the controller output or abrupt variation in the controller output by employing this particular structure, that is IPD structure. And this structure has been realized in Honeywell TDC 3000, which is a famous distributed control system, and this has been realized in distributed control system, that is in Honeywell DCS. So one can use IPD or one can use PI-D, which is proportional integral action based on error, and derivative action based on PV. Or so here you can get this transfer function by setting alpha by selecting alpha equal to 0, by setting alpha equal to 0 and beta equal to 0, one can get this IPD transfer function. These are all what I would say parallel form. The structure here is 2 degrees of freedom PID controller parallel form structure. Whereas in the second table, what I have reported is here is IPD series form PID controller. So 2 forms I have discussed with respect to single degrees of freedom PID controller. The first one is ideal or interacting or a parallel form I had mentioned. And the second one is a series interacting or a conventional type. And you have a 2 degrees of freedom PID controller, like conventional or a series form, and a parallel form available. The first one I discussed is a parallel one. The second one is the series. So here, this is basically a series form IPD controller structure. And this is again in the same Honeywell TDC 3000. This IPD is also available. IPD function block is also available. And user can use this if they want to prevent both proportional kick as well as derivative kick. So Honeywell TDC 3000 is a distributed control system. So this PID function block is available, and user can drag and drop this block from the library, and they have to configure the blocks. What I mean by configuring is the blocks, they have to set the proper values for K, theta, Y, tau, D, alpha, and beta, and that way they can configure and try to use these blocks and control process variables. So IPD series form PID controller, and here this is again series form PI-D, which is proportional action and integral action based on error, and derivative action based on measurement. So both single degrees of freedom PID controller available in the market. Similarly, 2 degrees of freedom PID controller also available in the market. And depending upon the type of, depending upon the application, the user can select either 1 degrees of freedom PID controller structure or 2 degrees of freedom PID controller structure, and they have to configure the parameters associated with the block optimally, and thereby they can achieve a satisfactory servo as well as regulatory performances. So now, before I discuss other topics, if there are any questions related to this, I'm happy to answer. And now I request the participants to raise questions. If there are any doubts, I'll be able to clarify. Participants, are there any questions? Are you able to follow?
Sir, one question is there. What is the gain in PID controller?
What is?
The gain in PID controller.
And what is gain?
What is the gain in PID controller?
Gain is nothing but see here. Okay, gain is nothing but KC. The term KC is there, am I right? That KC is nothing. That is nothing but the gain of the controller. So this KC. So your error will get amplified by that factor KC. So your input is error, and that error will get amplified by the factor KC, and that will affect your output. So U will be function of what? KC times error in the case of a proportional action. But KC is nothing but the proportional gain. Change in, or in other words, proportional gain is nothing but change in output by change in input. Is that fine? Are there any other questions?
Yes, sir.
And again, normally what we do is that we'll express in terms of percentage, and time, the integral time and derivative time are expressed in time units. Either it could be seconds or minutes. These are the units associated with proportional gain, integral time, derivative time. Okay. So,
sir, I have one question.
Yeah, please go ahead.
Good afternoon, sir. My question is, how shall we decide which controller is best for our system? Suppose I'm working on a DC to DC converter, second order or multi-order system. So how shall we decide which part of PID controller is best? What should be our approach?
No. See here, what is important here is either you have to see, like, for example, there are two performance which I had mentioned in my presentation. One is the tracking performance, whether your output should follow a set point profile if it is single degrees of freedom PID controller structure. Is it clear? Have I answered your doubt? So, which is dominant you have to see. Okay, so depending upon the, if both are both you have to take into consideration, that means both load change will be there and set point change. Both, if it is going to happen, then you have to use a 2 degrees of freedom controller structure and then select appropriately the value of alpha, beta, Kc, tau I, tau D, and n. So you have to select the values, and thereby you can achieve satisfactory performance. So there are 6 parameters. Okay, you have to tune them properly. There are many what I would say guidelines available. Like there is a handbook on PI and PID tuning rules available. You can refer and then properly set the values for your parameters associated with the controller structures. So depending upon the type of transfer function or tuning rules are proposed in the process control literature, you can follow that and set the values. That way you can achieve satisfactory performance. Is that fine?
So one more question is there.
Yeah.
Kindly give information for gain tuning using advanced optimization algorithms such as PSO or genetic algorithm.
So I would suggest here what I would say, you can use any optimization algorithm. I don't think there is any specific. I won't recommend any specific optimization algorithm. Okay, you can use any optimization algorithm you like. For example, you can use either GA or you can use PSO or any conventional optimization algorithm to minimize the performance metric, that is integral square error or integral absolute error. So I don't think, but what is more important here is you have to select the algorithm such a way that what will happen, you get a unique solution. You should get, irrespective of the algorithm, I would say if you have properly taken into consideration all the specification, you will get a unique solution. So that is very, very important. What is more important is you have to get a unique solution. So for that, like you have to, like if there are 3 parameters, if you want to properly select, then you need 3 equations, I would say. So specifications you have to properly select actually. Number of equations versus number of parameters. That is more important. So otherwise, you will get multiple solutions. So always what is important is one has to look for a unique solution. So for that, you have to properly select the specification. Specification is very, very important. That depends on how many parameters, okay, in your, what I would say, in your PID controller transfer function. If there are 3 parameters, then you need 3 equations. Minimum three, what I would say, specifications you have to impose. For example, your closed loop gain, your closed loop time constant, okay, settling time. So like that, so your user has to specify properly the specification. As a result, they get unique solution. Fine?
Yes, sir. You can continue, sir.
Yeah. So shall I proceed with my next slide?
Yes, sir.
So,
one question, sir.
Yeah, tell me.
Sir, regarding KC, there isn't any doubt. But while designing that value of a tau I and tau D, whether it should have been in between 0 to 1 or you can input value?
No, tau is time units. Time units.
It's
Yeah,
time
you can
unit,
say any.
while designing that is not known to us.
No, there is no. No, we won't impose any. We won't impose any limit. Okay, it should lie between 0 and 1. No. Okay, you can set any value.
Okay.
Normally, what we do is that we will set our integral time to be equal to that of process time constant. If you know the time constant of your process, then you can set your integral time to be equal to that of your time constant. Most of the tuning rules, if you see, tau I will be set equal to tau. So this is a thumb rule. Okay, normally we do actually. And most of the tuning rules, popular tuning rules, if you see, they'll set tau I equal to tau. Okay. So the other important point, what I want to say is that when we handle the control system course, like in the control system, when we handle a PID controller topic, so we have to teach that PID, okay, this industrial type PID controller has to be discussed in the class. For that reason, I go look at this. I have discussed in this short-term course. This is very, very important. And there are various forms of PID controller, and they have been realized in industrial type PID, and various types of transfer functions that are realized in industrial type PID that we have to discuss in the UG course itself. Because later when they join the company, so without knowing the type of transfer function, they will not be able to tune the controller properly. If they join an industry, they should know the transfer function associated with that PID. It will not be available in the catalog, so they have to go through. They have to see the specifications, PID specification sheet, understand what is the type of what type of PID controller or the form of PID controller. They should know what is the form of the PID controller. Once they know the form, then only they'll be able to configure the PID block accurately. Otherwise, by trial and error, they'll do that will lead to deterioration in the performance. So this is very, very important. We should discuss in that even in the UG class.
Sir, one more question.
Yeah.
In what case PI controller is prepared, sir?
PI controller alone, okay, if you want, see, for example, if you want to eliminate offset, and if it's a very fast process, the time constant is very, what I would say, very, very small value time. That's why we call it a very fast process. The process is responding quickly. Then we recommend a PI controller. If it is a dead time dominant process or a lag dominated process, we recommend a D action. Normally, if you want to improve the speed of response, D action is recommended. For example, in temperature control loop, we recommend it's a very slow process, so we recommend derivative action in temperature control loops. Whereas flow process is a very fast process, we won't recommend derivative action. We'll recommend either P or PI. The most preferred one is P controller, but sometimes you can also use PI controller. If you want to precisely maintain the flow rate at the desired set point, you can use a PI controller. Otherwise, no, you can use a simple P controller. So for a dead time dominant process, PID is recommended actually. PID controller is recommended.
One more question, sir. What are the different PID equations used in industry and distribution generation?
Which one?
What are the different PID equations used in industry and distribution generation?
Industry. No, all these are all what I would say the equation, the transfer function that is used in various products only I had mentioned in the slide actually. Okay. So, for example, in Foxborough exact model 761 product, in that industrial PID control, they have used this transfer function, the corresponding. Okay, in the second column, if you see the corresponding transfer function has been used. So, but this transfer function has to be converted into an algorithm. So, you have to convert that into an algorithm, which is easily one can do this. Convert this into a difference equation. Once you are able to convert this into a difference equation, then you can write a recurrence relationship will be there. So, you can easily convert this transfer function into an algorithm. Or you do simply a numerical integration, numerical differentiation, and just amplification. Then thereby you can achieve proportional integral and derivative. So, in industry, normally what they use is they use either Yokogawa controller or Honeywell, or okay, they buy controller from Honeywell or Emerson, Yokogawa, Foxborough, and that controller will be used in the industry. Here, what I have presented is what is the transfer function inside that controller. The transfer function could be classical one, or it could be an ideal one, or 1 degrees of freedom or 2 degrees of freedom. That engineer or operator should know. Then only they will be able to configure the blocks or the controller properly. Fine.
You can continue. You can continue, sir.
Can I continue?
Yeah, sir. Continue.
So, then, like in our department, jointly, like our department jointly with CDAC, Center for Development of Advanced Computing, CDAC Trivandrum, we had developed a product, an industrial type PID controller, jointly with CDAC, and we named it as iSmart. iSmart is an acronym, which is nothing but Industrial System Monitoring Autonomous Remote Terminal, it's a PID, industrial type PID controller. And jointly with CDAC, we developed this. The hardware was developed by Center for Development of Advanced Computing, that is Control and Instrumentation Division of CDAC, and various algorithms, that is various forms of PID controller have been ported onto this hardware. The hardware again, I wanted to inform this August gathering that the hardware was developed by CDAC, and the various control schemes have been ported onto this hardware. That is our MIT Department of Instrumentation Engineering contribution. And this it's a multi-loop controller, and here the specification associated with the iSmart controller has been presented in this slide. We have various types of communication interfaces: RS-232, Ethernet, USB, wireless, and then operating system that we have used is FreeRTOS. There are three like flexible input-output modules, AI, AO modules are there, and the processor, the processor which we have used, that is an ARM7 processor, has been used, the hardware. So, and we have realized various algorithms. The various forms which I had mentioned have been realized in the form of an algorithm, and we named it as an enhanced version of a PID controller. It can do the following functions: analog input channel processing, PID controller computation, analog output channel processing, alarm processing. All this, the PID algorithm can do this, can perform all these operations. And the EPID algorithm which we have developed, and it has been ported onto the hardware, has been validated on the experimental test rigs available in our process control lab. Here, what I have shown is the experimental test rig, and you can see here the PID controller which was jointly developed by CDAC and MIT, that is Department of Instrumentation Engineering. And you can see here scientists from CDAC, scientists and project associates who had worked on this project. Here you can see them. And we have experimentally validated our algorithm on the lab scale test rig, which is a simple level process. And you can see here in this slide, we have compared the performance of a conventional PID and an enhanced version of PID. It is nothing but an IPD, that is integral action based on error, and proportional and derivative action based on your process variable, that is P and D based on measurement. So which is nothing but a 2 degrees of freedom PID controller. So we have compared a single degrees of freedom PID controller versus a 2 degrees of freedom PID controller. And you can see here, we have introduced a set point change at around 40th sampling instant. We introduce a set point change, that is the blue one. And the green one is single degrees of freedom PID controller performance. And the red one is the 2 degrees of freedom PID controller performance. Here in the 2 degrees of freedom PID controller, we have set alpha equal to 0 and beta equal to 0. If you see here, both single degrees of freedom PID controller and 2 degrees of freedom PID controller is able to maintain the process variable at the set point. So the controller is able to take corrective action, and asymptotically, what I would say is that it approaches the set point. So there is no steady state error. There is no offset. But if you see the overshoot, in the case of a PID, relatively overshoot is high compared to what I would say a 2 degrees of freedom PID. Your overshoot is less. So, and if you see the settling time, more or less both are reaching the set point. That means your process variable is reaching the set point almost at the same time instant. So the advantage of an IPD controller structure is able to minimize the overshoot. Overshoot is less, and at the same time, both conventional single degrees of freedom PID controller and 2 degrees of PID controller, they are approaching the set point almost at the same time. So this is with respect to the output. With respect to the controller output, this is controller output. Here what we have shown is how the process variable is changing with respect to time, and the PID controller output is the evolution of PID controller output is present in the second figure. So this is controller output with respect to time, controller output versus time. This is process variable versus time. And if you see, at 40th sampling instant, we introduced an abrupt change in the set point. And because of this abrupt change in the set point, you will see an abrupt variation in the controller output. This we call it as a kick. You won't get a smooth variation, you get an abrupt change in the output of the controller. As a result, if the controller output, if this will go as an input to the final control element, that is your control valve or a pump, and if it is if you see a spike like this variation in the PID controller output, it will affect the life of the final controller. So you can see a smooth variation if you use a smooth variation in the controller output, if you use an IPD PID controller structure. So by implementing a 2 degrees of freedom PID controller, you will be able to protect the final control element, can enhance the life of the final control element. At the same time, you can reduce overshoot, and also you reach the set point at the same time. That's the power of what we have demonstrated here is the power of the 2 degrees of freedom PID controller compared to a single degrees of freedom PID. So there we have set alpha equal to 0 and beta equal to 0. You can vary the value of alpha and beta. So beta is nothing but B here. And the A and B we have used are alpha and beta. So by changing the value of B, what you can do is that if you set B equal to 1, you will get large overshoot. By reducing the value of B from 1 to 0, you'll be able to reduce the overshoot. Relatively, overshoot will be less compared to B equal to 1. B compared to B equal to 1, you will get, but almost all the, irrespective of whatever be the value of B, you will approach the set point at the same, almost at the same time. At the same time, you can get smooth variation in the control. So here what we have compared is a conventional PID. We named it as basic PID. IPD. IPID is when you set alpha equal to 0 and beta equal to 0, and 2 of PID, because you can set any value for alpha and beta, any value between 0 and 1. As far as alpha and beta, you should not exceed 1. Any value between 0 and 1 you can set for alpha and beta. And we have set alpha equal to 0.5, beta equal to 0.5, and we have generated these results. So let me explain the features of the algorithm, the algorithm which we have ported in the CDAC hardware. The algorithm can support basic type PID or IPD or PI-D or 2 degrees of freedom PID control structure. So that's the various types of PID controller computation that can be performed in our controller that are presented here. And then you can the controller can be placed in auto mode or in manual mode or in cascade mode. You can bypass control actions. Both position form and velocity form PID algorithm has been realized. And also you can reversing the action of the controller is also possible. For that provision has been given. And the problem associated with integral action is integral wind-up. That also can be prevented. So problems associated with the proportional action is proportional kick. That can be prevented. Problems associated with the integral action is integral wind-up. That also can be prevented. And similarly, the problem associated with the derivative action, which is derivative kick. So that also can be prevented in our by using our algorithm. And when you switch from auto to manual mode and from manual to auto, the mode transfer also should be bumpless. That also has been incorporated. So the mode transfer also, you will get a bumpless auto manual transfer if you use the PID algorithm. So these are all the features of the algorithm which we have developed and ported on the CDAC hardware. And this, the algorithm has been thoroughly tested on various lab scale processes, both in our MIT as well as in CDAC. Now this product is undergoing field testing at Tuticorin power plant, and I hope this product very soon will be marketed. It will be soon available in the market and it will be marketed by CDAC. And various other functions which this PID controller block. That is what all other functions it will do. That also here has been highlighted. We can do even alarm processing inside the PID itself, and so that is also incorporated. That is not only PID controller computation, PID control computation, alarm processing also it will be carried out inside the PID function. So the algorithms which I discussed have been ported on the ARM processor, and we have validated extensively our algorithm on lab scale process. And currently it is undergoing field testing at Tuticorin, and soon this product will be available in the market and it will be marketed by CDAC. So this is my so with that I've completed my first part. Now I will move to the second part. Here in my second part, I'm going to focus on experimental validation of PID control scheme. How to experimentally validate, how to design and successfully implement a PID controller. That is what I'm planning to focus in my in the second part of my lecture. So for this, for the design and implementation of PID controller, the process that I have considered is a simple, very simple process. It's a level process, and the shape of the tank that I've chosen it to be a conical shape, conical tank. You can have a spherical tank, so or a hemispherical, could be conical. The process, the shape of the tank that I've considered is a conical tank. And what is our interest here is we want to control the water level in this conical tank. That is our interest. Our interest is to control the water level in the tank, for which there is what is more important here is we have to sense the water level. So for the in order to measure the water level, we have used a level transmitter, which is a differential pressure transmitter based level transmitter, a DPT based level measurement. So in our lab we have a level transmitter, a DPT based level transmitter. With the help of this DP based level transmitter, we will measure the water level in the tank, and we do have a control valve, a pneumatically actuated control valve. With the help of this pneumatically actuated control valve, we'll be able to vary the feed flow rate into the tank, the inflow rate into the tank. So by adjusting the inflow rate into the tank, we will control the water level in this conical tank. And this the transmitter and the valve, they are interfaced to a PID controller. That is your level controller, industrial type PID controller. So this level transmitter is the interface with the level controller. Similarly, the control valve is also will be interfaced with the level controller. So the level controller will sense the information from the transmitter, will sense the water level. In turn, it will pass it to the level controller. Controller will take corrective action and will still send signal to the final controller, which is nothing but your valve. And the controller will take corrective action. It will adjust the flow rate such a way that the water level in the tank is maintained. It's a very simple experimental setup. Now I'm going to explain how to design a optimal PID controller and how to validate the design. That's my primary focus. Here, if you see, as the shape of the tank, it's a conical shape, and because the shape of the tank is conical, the area of the tank is not constant. It's a variable area tank process. As a result, the time constant of the process also will change. So the time constant is not constant. It will change. For example, if the water level is 10%, you will get one value of time constant. If it is at 50%, you will get another value of time constant. If you're close to 100%, that is 95 or 90%, you will get a different time constant because the area of the tank is not constant. Since the area of the tank is not constant, what you have to do is that you have to design and implement an adaptive PID controller, not a non-adaptive controller. Or when you change the operating point, you have to change the parameters of your PID controller. You cannot use the same PID parameters for all values of set point, because your the PID controller, because area of the tank is not constant. So in order to design and validate PID control scheme, let me explain what is the procedure that we have adapted. And this for research or for design and implementation of PID controller and industry, if you want to for research or for lab purpose, you can adopt this procedure. This procedure can be adopted. So the first step, what we have to do is that we have to select an operating point. And the operating point that we have selected is around 250. 250 is the operating point. It's a scaled value, the scale number between 0 to I would say 0 to 450 is a scaled number. So we have selected the operating point to be 250 for output and close to 340 for your input. Input is nothing but the controller output. So if the controller output is maintained close to 340, then your water level will be maintained exactly at, I would say, at 250. That is my operating point. That is the meaning of an operating point. So you have to select an operating point. So first we have selected the operating point by giving 340 as a value. This is your controller output. By setting 340, that means setting the output of the controller close to 340, you are able to maintain the water level in the tank at 250, which is a scaled value. And then what we did is we increased and decreased the controller output. We increased by a small amount and then we maintained it. Later, it was brought back to again 340. Then we reduced it. Then we brought back to 340. So some random step-like variation in the control output were introduced. And what you see here is how the water level is changing with respect to time. The corresponding level variation with respect to time is shown in blue color. The blue one is the level variation with respect to time for, this is for the variation in the flow rate, for the inflow rate. Since the inflow rate has increased, the water level also has increased. Here, if you see, the inflow rate has reduced actually. As a result, your level is decreasing. So here, what is important here is you have to, this is what we call it as an open loop study. You have to select an operating point, try to maintain the process variable at that operating point, then give a small perturbation around that mean value, which is 340, close to 340, increase and decrease your controller output, and see how the output is changing with respect to it. Then using this data, using this input output data, the green one is the input data, blue one is the output data. Using this input output data, what you try to do, you try to build a transfer function. And there are many, like how to estimate the transfer function model of a system. There are many algorithms available in the literature, system identification algorithms. Use proper system identification technique, and then try to, what you do is that determine the transfer function of the system. And so the transfer function, which it's a first order, simple, it's a first order process. And we have estimated the parameters of the first order process, gain and time constant of the parameters associated with the first order transfer function. We have estimated to be 2.08. Estimated value of gain, process gain is 2.08, and the time constant is 28 seconds around this operating point. It is around this operating point. But so we have estimated to be 28 seconds. And then what? So here, so this is the process. So the process at the operating point, that is the operating point, the system is behaving like 2.08 divided by 28 s plus 1. It's behaving like this. Behaving like a first order process with time constant 28 seconds and gain 2.08. What is our interest is now, we wanted to design a PI controller such that the closed loop transfer function, what we wanted to achieve is 1 by 14 s plus 1 is what we would like to achieve. So the open loop transfer function is 2.08 divided by 28 s plus 1. And in the presence of controller, like after designing a controller, what we wanted to achieve is 1 by 14 s plus 1. That is nothing but the transfer function relating PV and the segment. If you do a block diagram reduction of this, you will get this. 1 by 14 s plus 1 is what we wanted to achieve. So in order to achieve 1 by 14 s plus 1, we have set Kc as 1 and tau I equal to 28. So okay, so here what we want to do is, we want to reduce the time constant of the system is 28 seconds. We don't want that. We wanted to reduce it by half actually. Time constant of the closed loop system should be 14. So we have chosen 14 seconds as the desired closed loop time constant. And in order to get this, we have set the value of Kc and tau I as 1 and 28. This, like the approach that we have used is a synthesis method. If you follow a direct synthesis method, you can easily find the value of Kc and tau I given the open loop time constant and closed loop time constant. This is called synthesis approach, using a direct synthesis approach. In the direct synthesis approach, what we require is open loop time constant and closed loop time constant. By providing these open loop time constant and closed loop time constant, we can get the parameters associated with the controller, which is Kc and tau I. And we have set those values in the PID controller. And here what you see is like initially the process variable was maintained at the desired operating point, which is 240. Then we introduce a set point change from 240 to 260. And you can see here the controller is taking corrective action and it's reaching this desired set point at close to what I would say 700 seconds. So 700 seconds. So that's the time constant of the process is 14. So 14, roughly what I would say 15. So within 75 seconds, what it should do is 5 times the time constant is the settling time, should reach within 5 times the time constant. So you can see here within 75 seconds, is able to reach the set point. The corresponding controller output is shown here. Then what we did is with the same controller settings, this is our nominal operating point. This is our nominal operating point. Then we introduced large change in the set point. And also we introduced further we moved away from the operating point. So the nominal operating point is 240. We move away from the operating point. We moved from 240 to 310 or 320, and then from 320 we moved to 370. So you can see here. So if you move away from the operating point, the system is not giving satisfactory closed loop performance. It has to behave like a first order system. It's not behaving like a first order system. Around the operating point, it is behaving like a first order system. If you move away from the operating point, it is behaving like a second order system. You see there is a overshoot, undershoot, and finally it reaches the set point. So if you're moving away from the operating point, the system is not giving satisfactory closed loop performance. If you're close to the operating point, you are getting satisfactory performance. If you move away from the operating point, it is not giving satisfactory performance. The reason why it is not giving satisfactory performance is because the time constant is changing. As a result, you should not use the same controller settings. You should not use the same value of Kc and tau I. So whereas we have used the same value of Kc and tau I at this operating point as well as at this operating point. So to get satisfactory closed loop performance, you have to modify the parameters of the PID controller here as well as here. So in order to design PID controllers at different operating points, what we have to do is that again we have to conduct open loop test, collect data, then we have to build a model. So using this model, input output data, we'll try to build a model around this operating point, around 250, then around 300, then around 350. At 3 different operating points, we have developed models. That means we conducted studies, open loop studies, and then we build models. So you can see around operating point 250, the process gain is 2.08 and the time constant is 28. Around 300, there is no much variation in the process gain, but time constant has drastically increased. And if you move away from the operating point, that is from 250, that is your nominal operating point. If you move away from the operating point 350, process gain almost, it has not changed much, but whereas the time constant has increased. So since your process parameters are changing, when you change your operating point, you have to update the controller parameters also. Because your time constant is changing. So as a result, you have to modify your controller parameters, then only you will get satisfactory performance. That we did. So the parameters are changing, Kp and tau p are changing, but there is no much variation in tau p. But whereas Kp is not changing that significantly, whereas tau p is drastically changing. So what you have to do is that accordingly you have to modify your Kc and tau. That we did. Okay, and then you can see. So this is the variation that we have introduced, and now at all operating points, if you can see, the controller is behaving satisfactorily. There is no overshoot. It's behaving like what I would say, a delay plus first order system. Not exactly a first order system, but there is no overshoot, and it is able to reach the desired set point satisfactorily. So when we move from 240 to 260, then 320 as well as 370, we are able to get satisfactory closed loop performance. And we have used different values of internal gain because the parameters has to, we cannot use the same value of internal gain throughout the operating point. As I had mentioned, you won't get satisfactory performance. So we used different values. As a result, we are able to get satisfactory closed loop performance. This we call it as gain scheduled PID implementation. So it's one form of an adaptive PID controller we implemented. As a result, we are able to get satisfactory closed loop performance. Any specific doubt with respect to this? Any specific doubt with respect to this part, that is experimental validation of a PID controllers or a validation of a PID controller scheme?
Yeah, participants can raise the question.
So, any specific doubt?
I think so. I think they at the end they will ask the question. You can continue the session, sir.
Yeah. So let me once again, I wanted to repeat here. So you have to select the operating point, then build a model around the operating point, meaning like you have to get the transfer function, then investigate whether the parameters are changing significantly. If they are not changing significantly, you can use the same controller settings throughout all operating at all other operating points. Otherwise, what you have to do is that you have to update your controller settings as you move from one operating point to another operating point. That's the message which I wanted to convey here. The last part, I think I will not be able to explain in detail because we are running out of time, but let me explain how to design a simple model-based control scheme for a stable linear system. As well as, but we have extended it for non-linear system. You can refer to our papers in the reference. You can see our in the reference. I have indicated papers that we had published in peer-reviewed international journals. You can see. So basically, what so far what I have explained is for a given process how to design a PID controller. How to design a PID controller. GP of it is the transfer function of a process. So for that, how to design PI. You can design PI controller or you can design PID controller, how it can be experimentally validated. And that, okay, I got explained. So what is more important here is we have to satisfy the specification. The specification which I had chosen for the conical tank process is the settling time. So or a closed loop time constant, whatever. So that we wanted to satisfy. At all operating points, what we want to satisfy is the desired closed loop time constant. So in order to satisfy the desired closed loop time constant, we modified the controller settings, the parameters. That is the integral gain we modified. So now let me explain how to design a simple model-based controller. This PID is a non-model-based controller. Let me explain how to design a simple model-based controller. So for that, here the same PID controller which was shown in this slide, that I'm trying to represent a PI controller in the form of like what I would say that I've realized that the PI controller with the help of two blocks. KC times error, that is your proportional part, plus I'm trying to realize the integral action. The integral action here has been realized as a positive feedback. You can see here as a positive feedback around a lag element, around a lag. So this you can refer to Astrom's and Aguilan paper. Refer to his book actually. So a PI controller can be realized in a reset configuration. This is what we call it as a reset configuration based PI controller realization. So with the help of a gain block, a lag block, adder, and what I would say a saturation block, can realize this reset configuration. This is nothing but a PI controller. So this PI controller has been realized with the help of these blocks. So one can easily realize this in MATLAB or in Simulink. This can be easily realized. Okay. So with the help of this PI controller, you can control any process. The process that I have considered here is a GP. GP is the transfer function of the process, and you can control with the help of this PI control. And if you see here, irrespective of whatever be the order of the process, could be first order, second order, or a process with get time, integrating type process, whatever be the order of the process, if you see inside the controller, a first order transfer function is used. So this is nothing but a PI controller transfer function. It is realized. Okay. So this is, so the integral action has been realized as a positive feedback around a lag. So this is basically a first order block. Irrespective of whatever be the order of the plant, a first order lag is used to realize an integral action. And with the help of this, by properly selecting the value of Kc and tau I, we are able to get satisfactory closed loop performance. We can satisfy servo performance and regulatory performance. So in a nutshell, what I can say is a first order model with a unity gain is implicitly used in a PI controller, regardless of order of the process to be controlled. So instead of using a first order gain-free part of the first order block, first order model, what we had suggested was, why not we use a gain-free part of GPFS. If GPFS happens to be a second order transfer function, then we will use the gain-free part of the transfer function inside here, inside this block. Inside this block, we will use a gain-free part of the second order transfer function. If the system to be controlled is a delay plus first order, then we will use the gain-free part of that. So instead of using a first order lag, what we had suggested was to use a gain-free part of GPFS. As a result, you won't get a standard PID controller, but okay, the controller transfer function will depend on the process transfer function. It won't be a standard PID, but it will depend on GPFS. So it's a model-based controller, a simple model-based controller, and we validated. And if you see, so here we are going to use the gain-free part of the transfer function. As a result, there is only one tuning parameter, which is Kc. So in our proposed control scheme, there is only one tuning parameter, Kc. By properly selecting this value of Kc, one can achieve satisfactory close to performance. And then this we tried it on various processes. So I will explain. So the process that we have considered is a fourth order process model with gate time. This is the process that we have considered. And we have designed a model-based controller. That means the gain-free part will be used instead of a first order lag, we have used this gain-free part of this GMFS in our controller. And then we have set the value of Kc as 0.85. And at the design stage, to determine the value of Kc, we have used MS as the criterion. So MS is the criterion that we have used. So that is the performance index which we have used is a MS, which okay. So here we are trying to satisfy both performance and robust stability. That's our performance measure. MS is the performance measure. Maximum sensitivity is the performance measure which we have used. And we have chosen MS to be 1.6. And and by setting MS equal to 1.6, we determine the value of Kc as 0.85. And you can see the performance of our proposed controller and various other controllers available in the literature were compared. We have compared IMC, we have compared SIMS PI, SIMS PID, and proposed with set point filter for both set point variation as well as load variation. And you can see here the IAE value of our controller, the integral absolute error, which is the performance metric which we have chosen. That IAE is less compared to other control schemes. For us, the IAE value is 5.74. For our control scheme, IAE's value is 5.74, whereas for other control scheme, it is 6.70, 10.2, 7.87, and 7.67. So with the help of our proposed control scheme, we were able to get a lower value of IAE. So you can see here, as a result, your process variable is approaching the set point quickly. The blue one is the proposed one, the green one is the proposed one with set point filter, whereas the red one is the IMC, and IMC controller is taking longer time to reach the desired set point. So we have given a set point variation, set point change from 0 to 1, and the process variable is reaching the set point. Similarly, we introduce a load change here. Controller is taking corrective action and bringing the process variable back to the set point. Again, the green one is reaching the set point as quickly as possible. As a result, your IAE value will be less. This is for IMC. Similarly, we have compared SIMS, PID, and PI. Here again, our proposed scheme outperforms SIMS, PI, and PID. We tried it on various other transfer function, means process with dead time and a 0 lying on the right hand side of the plane. Again, you can see here IAE value for our proposed control scheme is 9.5, whereas for IMC it is 18.5, 14.18 for SIMS PA. For SIMS PA it is 12.95. So for set point change, for load change also you can see our control scheme is able to give lower value of IAE 9.63 compared to IMC, SIMS, PI and PI. So what here we have demonstrated is with the help of a simple model-based scheme, model-based control scheme, that is, instead of using a first order lag, if you use a gain-free part of the transfer function in your control law, you are able to get satisfactory set point performance as well as load performance compared to IMC, SIMS, PI and PI. That's what I wanted to convey here. It's a very simple model-based control scheme. And so here I've shown the process and controller responses for the higher order process. Here for process with dead time and right hand side 0. So the process and controller responses are presented. And then we have also carried out experimental validation, and the experimental validation also reported in this slide. So we validated our control scheme on a lab scale level process. We have compared the performance of our control scheme with that of SIMS PI, high-res Lumen PI controller settings, and you can see here that is the blue one. It outperforms SIMS PI as well as high-res Lumen PI controller settings. Are there any questions? So what I had explained is how to design a simple model-based control scheme for which the structure which you have used is a PI controller structure. Instead of using a first order lag block, we are using gain-free part of the transfer function inside our inside that feedback path. That is and then the performance measure which we have used is MS, maximum sensitivity. And by satisfying that, we have determined optimally the value of controller settings, and we have assessed the performance of our controller by giving set point change as well as load change. And the control scheme is able to give satisfactory closed loop performance, that is servo performance, as well as relative satisfactory load performance, disturbance rejection performance. So if there are any questions, I'll be able to answer. Otherwise, whatever I wanted to cover, I've covered. So there are 3 parts. I've covered all the 3 parts. And if there are questions
from the participants, or else you can put in the chat box. Hello.
Yeah.
Santosh Gupta. Gupta. If you have the questions, raise the question. Hello. Any questions?
Unmute yourself.
Santosh Gupta,
Sir.
unmute yourself.
Sir, no question.
Okay. Yeah. Okay, sir. Thank you.
If there are no questions, I would like to thank once again the department and Professor Prasanna Kumar for this opportunity. Thank you very much. Wishing all the participants a very bright future.
Thank you, sir. Thank you, sir. Bringing from the non-interacting to interacting session. One question is there, sir. Sir, you can please compare model-based PID controller with sliding mode controller.
It can be done. It can be. There is no problem. If you want, you can compare any control scheme.
Okay, sir. Thank you, sir. Bringing us from the non-interacting to interacting. Probably would I think now the PID controller is adapted to our system. The disturbance is lower now. In the morning session, you got a lot of disturbance. Probably after your session, that adaptedly that PID controller is adjusted to our system. That
Okay.
unknown person is, I think, went out after seeing that PAD equation and other things. Thank you, sir. Even though you are
Thank you very
busy
much.
scheduled, you are
Thank,
agreed to giving the talk. Thank you, sir. Thanks once again, sir.
thank you very much. Thank you. Thank you. Thank you all.
Thank you, sir. Now I'll request to participants. Already we sent second session feedback form. After filling that one, we'll start the session around the third session 2:25. Please log in. Thank you.
Prasanna Kumar, please share the feedback also. Thank you.
Yeah, sir. Definitely, sir. I'll share that one, sir. Thank you, sir. Thanks. We'll rejoin the session around 2:25. Thank you.
Shall I end the meeting, sir, Professor?
Yeah.
5 minutes I have to wait.
Yeah,
Right.
5 minutes you have to wait. Yeah, why, that they have to copy that Google form. I think BP sir is there. Sir?
Sir?
Sir? BP sir?
ఏంటి ఈ ఇయర్
Sir is there. Sir is there. Sir is there. Professor Prasanna Kumar, sir is there.
Hello? Hello?
Yes, madam.
Actually, sir, na unmute ಮಾಡಿದೆ. Now I think sir is unmuted.
Okay.
Sir, we can't hear you.
Sir, BPS sir? Hello?
Mhm.
Sir.
Hello.
No interruption in the second session, sir. Second session went very nice, sir.
Very good.
Hello.
Go ahead.
Very good. Even he tried in the second session also to enter. We locked him and we expelled out him. Okay, sir. ಮತ್ತೆ ಸೆಕೆಂಡ್ ಸೆಷನ್ ಆತ ಎಂಟ್ರಿ ಆಗಿ ಟ್ರೈ ಮಾಡ್ತಾ ಇದ್ದ ಸರ್ ಬಟ್ ವಿಲ್ ಎಕ್ಸ್ಪೆಲ್ ನಿಮ್ ಇಲ್ಲ ಸರ್ ಈ ಸಲ ಏನು ಡಿಸ್ಟರ್ಬ್ ಆಗ್ಲಿಲ್ಲ ಸರಿ ಆಯ್ತಲ್ಲ ನಾವು ಅದನ್ನ ಈಗ ಎಲ್ಲ ಅವರೆಲ್ಲ ಸಾಲ್ಟ್ ಮಾಡಿದ್ದಾರೆ ಈಗ ರಿಸಾಲ್ವ್ ಮಾಡಿದಾರಲ್ಲ ಈಗ ಓಕೆ ಸರ್ ಓಕೆ ಸರ್ ವಿಲ್ ಸ್ಟಾರ್ಟ್ ದಿಸ್ ಥರ್ಡ್ ಸೆಷನ್ ಅಟ್ 2:25 ಸರ್ ಮಹೇಶ್
Yes.
We can end this session on the chat box ಅಲ್ಲಿ ಹಾಕ್ಬಿಡಪ್ಪ
Okay, okay.
ಸೆಷನ್ ಯಾವಾಗ?
ಹಲೋ
ನೆಕ್ಸ್ಟ್ ಸೆಷನ್ ಯಾವಾಗ ಪ್ರಸನ್ನ?
2:25 ಗೆ ಮಧುಸೂದನ್ 2:30 ಗೆ 2:25 ಸ್ಟಾರ್ಟ್ ಮಾಡಿ 2:25 ಓಕೆ ಮಧುಸೂದನ್
ಓಕೆ ಥ್ಯಾಂಕ್ ಯು.
So any clarification from anybody? Can we end?
Yes madam, we can end.